Hello, I'm Mike McCulloch. So today I've come to the local A road or motorway to try and explain something that is quite unique to quantized inertia, and that's some doubts about what happens to objects close to the speed of light. So you probably know that special relativity has something to say about this. According to special relativity, the closer you get to the speed of light, the greater the inertial mass becomes, and it follows an equation like this that you can see here. So you can see from this equation that if v, the speed of the object, is equal to the speed of light or close to it, then 1 minus v squared over c squared becomes 0. You get a division by 0 and you get infinite mass implied. So this seems to mean that special relativity by itself precludes getting up to or beyond the speed of light, because the inertial mass becomes infinite, and that means that things become impossible to accelerate. So this means that as you get closer to the speed of light, your velocity should be more or less constant. But it's characteristic of quantized inertia that the inertial mass is caused by unreal waves. And the wavelength of the unreal waves is determined by the acceleration. So if you get up to the speed of light and your acceleration becomes close to 0, because you've got masses of inertial mass, then the unreal waves that you see will be longer than the cosmos, and so by quantized inertia they will be disallowed, and so your inertial mass will collapse again. So this implies that quantized inertia has some modification to make to this prediction of special relativity, and you can work out what it is by writing the inertial mass, but this time including both special relativity and quantized inertia. So that's shown here, and so it's quite a complicated expression, but if you write this in terms of the acceleration, you get this, and then if you multiply both sides by the denominator on the right, you get an expression like this, which tells you that the acceleration that you get is equal to the first term, which depends on the force, which is the usual one, is very similar to what we had before, what was assumed before, and then we have another term. So the acceleration is this first term plus 2c squared over theta. So I hope you can see that if you have the first term by itself, this means that if v equals c, then no matter what force you apply, this will always be multiplied by 0, and so you won't get any acceleration, which is fine. That's special relativity. But the second term, as I intuitively alluded to before, messes all this up, because it implies that no matter, even if you have 0 force, you will still get an acceleration, no matter what special relativity is doing. And in fact, the second term will be boosted slightly, well, quite a lot actually, because as you approach the speed of light, the cosmic scale will reduce because of Lorentz contraction. So this second term will be boosted. So I gave a talk a long time ago at the 100-year Starship Symposium in Florida about this, and argued that what we can do is try to boost this second term, and the way you can do that is by producing a informationally closed region around the body. You have a what I call a metamaterial shell, which reduces the cosmic horizon from the usual cosmic horizon to this shell, which can be much smaller, and which can boost this extra acceleration, which is, if you like, relativity proof. So does this occur in nature? Well, it could be, and I've mentioned this in papers, that galactic jets are an example of this. because there is some indication, despite the paper of Reese in 1966, that galactic jets do travel faster than light. But of course, this is going to be very hard to argue because of causality and that sort of thing. Anyway, so all I'm saying with this video is that quantized inertia slightly modifies events close to the speed of light, and this might be usable. Okay, well, I hope you've enjoyed this short, and I look forward to seeing you next time. Oh, and I should say that I published a paper on this, which is shown here. Okay, bye.